Hi, I'm Peter Kellner, the organizer of 15 years of Silicon Valley Code Camp, and this now is our third Silicon Valley Code Campfire, and this one's focused on software architecture. You can probably tell that I'm here in Borrego Springs, still, and liking it a lot. Tammy and I have been here for about 4 years now, and even though we love Silicon Valley, we actually love Borrego Springs more. We will come back to visit, but we're here for a while. The biking is great, the weather is great, we just love it all around. Anyway, back to our current conference. Our first session is Ron Kleinman. Ron's currently an instructor at De Anza College and a retired architect, though I'm not sure how retired he is. He always seems incredibly busy. He's going to basically go through a typical scenario that an architect would face when building an app. His app that he's going to go through has something to do with college registration, and I'm sure you'll learn a lot of the things that you run into if you actually become a software architect. Incidentally, Ron has our most popular video on YouTube with currently over 400,000 views, which is totally not a surprise because Ron is a really good presenter and what he presents is really good. So our second speaker, Juval Löwy, who I've known for a very long time, is awesome. I met Juval probably 15 years ago when he was teaching a class on architecture, and I just learned a ton. Then 10 years ago, I was at an MVP summit and we were in a language review where basically the creators of C# were explaining what they were currently doing and what they were.
Good morning. This being the Silicon Valley Campfire dedicated to software architecture. In this talk, we will discuss how a software architect thinks about an application as opposed to how a programmer thinks about implementing that application. Essentially, for most folks here, we're going to discuss what you don't know in terms of application development. My background, my name is Ron Kleinman. I've been an instructor at De Anza College for over 30 years. I've started during that time many courses, one of which makes me sound like a doctor. I gave the first C-section at De Anza. In this particular case, we're going to be analyzing a complex software application from the point of view of the software architect. So to understand what a software architect does, let's look at what an architect does, the kind of things that they do in architecting a house. You start with the home buyer's functional specification. In this particular case, the buyer says, I want this, a 3-bedroom, 2-bath home, 2,000 square feet, large living room, and all of the requirements that the buyer is interested in that house, about the master bedroom suite, solar heating, security system. You're a building architect. You must build that house. Where do you start? Where do you begin? You've got the specification. Where do you start? That's not where you start. Obviously, there's some thinking that needs to be done between the point that you hear the specification and the point that you say to the carpenters and the electricians and the masons, this is what you do to build that house. So what does a building architect actually do when starting construction or design of a new building? So you have the roles you've got. There's a customer, planning documents, physical system decisions, and the actual installation. And for a new home, they break down into the buyer, who is the one that comes up with the functional specifications for the house, the architect, who takes those specifications and creates a series of blueprints that are used to convey the thinking of the buyer to the people who are going to be actually building the house. The general contractor makes decisions like looks at the blueprints and says, oh, what kind of piping are we going to use? What kind of wiring are we going to use? Actually makes the specifications real to the specific house. And then finally, the workers are brought in, the plumbers and the electricians working under the general contractor to implement the blueprints that the architect defined based on the customer's input. And that's how houses get built. So you're an architect, and you've got the functional specification, as we've discussed. You have to build that house. What is the first thing that you do? What is the first thing that you do? Well, you need to identify the actual components. The functional specification usually is from the point of view of the customer, not the implementer. And your job as the architect is to translate that set of instructions from the customer into something that the implementers can build. Start by asking questions. In the example that we gave, there was a specification for a house. The architect looks and says, shouldn't the house have a kitchen? What about closet space, a laundry room? Those are things that every house needs to have. Wasn't in the functional specification that the customer wrote, and has to be added in because otherwise the house can't be built. You need to look at the interactions between components. What are the sizes of the bedrooms? Where are they located? What about the high level requirements? Security is a word that's used both for building houses and for building applications. But what kind of security? In the case of a house, it could be anything from an electronic photo system that scans the doorway to in a less safe neighborhood, bars on the windows. There has to be capacity, things that the general contractor would get involved with. The capacity of the water heater, the piping, and the zoning. There are zoning requirements. It must fit in with existing structures in the same way that an application must fit in with the other applications running in the corporate enterprise. What are the trade-offs? Some applications require more money. Others require it has to be done by a certain date. And then each individual component has to be analyzed. What is the exact size? What is the material? Information that the implementers are going to need in order to construct that house. So what does a software architect actually do when starting to develop a new software application? And it turns out it parallels what the architect did with the house. The application, the buyer becomes the domain expert. If you're designing a system to automate a library, it's the librarian. If you're designing a system to handle enrollment at a college, it's the registrar. And they have a set of functional specs, the things that the application needs to do. The software architect takes that functional spec and generates, instead of blueprints, generates a series of UML artifacts. That's Unified Media Language artifacts, which convey the thinking of the domain expert in a way that the developers can actually implement what the vision of the domain expert is. You have typically on a project, there's either the software architect or the main project designer worries about issues that transcend the particular application. Issues like data store. Are we going to have it in a central IT facility, or are we going to put the application in the cloud? What about security? What security schemes are we going to use? And these transcend a particular application, but they're like the zoning requirements. They're the things that you have to do because you live in a certain neighborhood. And finally, we have the developer, the software programmer, who comes in to code and debug that particular pieces of the application, call them objects, that have been defined. And so taking it together, you have a house. So let's look at an example of an application and see what the thinking is that takes it from the functional specification and starts it on the road toward an application. So here is the description of a college enrollment system. And it's particularly tied to De Anza, which is the college that I teach at. De Anza courses are offered by departments, available quarterly. There's an identification number, and it has a name like object-oriented analysis and design, description, number of credits, things about the course that's being offered. Each course is assigned set of times when it meets, find a teacher who is willing and able to teach that course. And I'm reading this because this is the functional description of the application that we're going to be looking at. Assigned a room, students may enroll, sections can be open, waitlisted, or full. If a student is accepted, her attendance will be tracked and she will receive a final grade. You take this description, and the question is, you must produce a working system. Where do you begin? And you don't start with the code in the same way that you didn't start building the house based on the functional description. You don't start coding based on the functional description. You have an architect who starts looking at it and moving the process forward. The first step that the architect does, software architect, identify all the components, ask questions, take the functional specification, and try to make it into something that you can implement. This involves direct talking to the domain expert to identify and document the issues that are going to be relevant to that application. So the first thing that you do is you need to define the words. Words have meaning, and the first step toward implementing an application is defining the application vocabulary. What do the words mean in the context of this application? So we highlight the words. We look and we say, there's college. That's an important thing for an enrollment system. Courses that are taken, departments, teachers, rooms, and students. Those are going to be the basic abstractions that underlie what the application is going to do. And so we have 6 basic abstractions that we would be making into objects in an object-oriented solution for the enrollment application. Then we start asking questions. And it should be noted that a software architect can come in the morning and stare at the ceiling and go out to lunch, come back, stare at the ceiling, go home, full day's work. Question is, what is a software architect thinking about? Here are some of those things. Can you assign a room and a teacher to a course? Well, the thing is, a course might be taught in several rooms. It might be taught by several teachers. So which teacher or room is assigned to teaching that course? Can a student enroll in a course? Well, sure, but it's being taught in several rooms with several teachers. So what is a student actually enrolling in? And you realize there's an abstraction missing here. It's not that we've been talking about enrolling in courses, teaching courses, but course doesn't have that meaning in the application that we're defining. There's a new abstraction here, something else that's hiding in the details of the application that the software architect needs to identify. And it's a section. A course has many sections of a course. Each section has a room, has a teacher, and has students. Essentially, a section instantiates a course. A course might be taught in the winter, and there in a given term, there might be no sections of that course being taught at all, which means no one enrolls, no one teaches it. Or you could have one section, or you could have multiple sections. And so when you're saying, I'm enrolled in a course, what you're really saying is, I'm enrolled in a section of a course. And that is changing the vocabulary of the application, but it's also getting it to be something that can actually be implemented and solved by an application. Second question, teachers, rooms, and students all must detect scheduling conflicts. Student can't take 2 sections at the same time. Teacher can't teach it. Room can't hold it. How do we avoid writing duplicate code? Because we've got the same scheduling issue. Does this section match my schedule? So we have to write schedule conflict detection code that says you can't do this because it conflicts with this other section. How do we do that? Well, we have 3 choices. We can write the scheduling conflict code once and cut and paste it into the other 2 places that we need it. We can write a new object containing the code, or we can write a new object containing the code which is used by all three applications. And in this particular case, it makes the most sense to have every object contain its own schedule object. So the schedule object doesn't even apply necessarily to the enrollment application. This is an application that knows how to merge two schedules, how to subtract out one schedule from another if the course is dropped, knows how to do all of that without knowing that much about our application. One of the things that a software architect uses to his or her advantage is when you're faced with a problem that you have to deal with in an application, one good approach is to wall it off behind an object encapsulation and assign someone else to worry about it so that no one else has to think about how to solve that particular application. So we started with these 6 abstractions or objects, and we've added 2 more. We've added schedule, we've added section. Now we go to lunch. Now comes the afternoon. We start thinking, what is a prerequisite? A prerequisite is something that you have to complete before you can enroll in a section, actually in a section of a course. So you can't take CIS 2 perhaps before you've taken CIS 1. And we're trying to define what that is. Is it a course, a section? Is it a string containing the name of the course? Is it a different object entirely? We're an architect. Before the programmer gets there, we have to understand the meaning of the word prerequisite. Otherwise, it's impossible to implement. And we have to do that in a way that matches the expectation of the domain expert. So we think about it. Suppose we say it's a course. Well, okay, prereqs have departments and course identifications. You must take CIS 1 before you take CIS 2. Course can have multiple prerequisites. You have to take English whatever and math whatever and CIS before you can take CIS 2. A prereq can have multiple prereqs. If you have CIS 1 might depend on some things. So those will be the reasons for making prereq into a course. There's no reason for making it into a section. Prereq is always focused on was the material covered. A simple string. Well, you say, okay, CIS 1, it only has to be a simple string inside of CIS 2, or a new type of object. So let's think about it some more. Look at the catalog of a typical college. Prereqs have types. They're advisory or they're mandatory. They may be totally independent of other courses. An example would be for CIS 2, prior experience with the object-oriented language. That's not a course prerequisite. It's just a prerequisite for a course. So we start thinking that, oh, prerequisites are objects. They may have a type, advisory or mandatory. They may be a combination of multiple courses. They may have a string. This is the kind of object a prereq is. Let's wall it off behind object encapsulation and give it to a developer to do. But we now understand how prereqs impact the application that we're doing. This is the thinking that goes into taking that specification and actually making something that can be implemented by developers. So we've gotten this far. And this is where we are at this point in time. What we're looking at is a UML artifact. The artifact shows, in terms of what we've designed so far, that we have a college which has departments. One college has N departments. A department offers N courses. A course has prerequisites. The department employs teachers who have schedules. That's the red S. It owns rooms. In particular in De Anza, the particular room is owned by the department, not the college. And then we have sections. One room locates N sections, one teacher instructs N sections. At this point, you could show this diagram to two people. You could show it to the registrar and say, is this what the enrollment system is dealing with? And the registrar would say, yes. This is a very different uh, uh, diagram than would have come from the original functional description. It's much more intuitive in terms of what is actually going on with the application. And it is also something that a developer could look at. The developer looks at this and says, okay, I see 1, 2, 3, 4, 5, 6, 7, 8 objects that have to be implemented. I sort of have an understanding of how they relate. I have a beginning idea about how this application should be implemented. At this point, we're going to stop, let some other speakers go, and we'll come back and take this to the next level. Thank you very much for your time. It sounds much more impressive than it was. There was no surgery involved. Thank you.
Okay. Just checking with Peter to make sure that our stream is working. I think it might be black, but Peter's going to check on that. So you're getting some love from your De Anza students here in the stream.
Some of them came.
Yeah.
Okay.
Anyway, I'm gonna start with the first question from Corvin, which is, what are the overlaps and differences between an architect and product designer / manager?
Okay, well, the difference is typically an architect is working on a project that has functional specification and is conversing with the programmers. The architect is the bridge between what the customer wants, or I guess the marketing team and the programmers. Marketing and programming they're different. There's very little, the marketing division has a vision for what they want in that product, and the programmer says, hey, what objects do I have to program to? What are the interfaces? And there's that gap, which is where the software architect comes, and very much like a regular architect in builds skyscrapers, takes the plans and converts it into something that can actually be constructed by the people who do that work. So that's really the difference. The product designers and so on, they're at a much higher level, and they're figuring out what the product has to do. But the difference between knowing what the product has to do and understanding what objects have to be there and how those objects have to interrelate, that's really the difference, the gap that the architect fills, establishes the vocabulary for the project, in which the same words, a given word has the same meaning to both the marketing people and the customer at one end, and to the programmer and developers at the other end.
Yeah, and you talk about the importance of asking questions to identify the components of a functional specification.
Yes.
And specifically direct interaction with the domain expert. Well,
Yes.
What if it's not clear who that domain expert is, or what if there's multiple people who think they're the domain expert and they don't necessarily agree on the domain? How does that part of an architect's job work?
So there's typically the applications we're talking about here are the applications that sit inside of an enterprise. I mean, you can break applications up into two groups. One is the Silicon Valley kind of application where the application runs alone. Facebook, Google, they run alone. The second class of applications is the applications that run inside of an enterprise, like the enrollment application of the school of facilities management or the human resources application, all of them working to play together in order to make the enterprise run. And it's that second class of application that we're talking about. And when you're looking at a product, there are two kinds of end users. If you're working for the school, that's when a lot of people can say you're doing an application, it should work this way, it should work that way. When you're working for a company, there's usually one person who has a contract that we need this system, and you're working toward that contract. So there's only one voice at the other end. They're trying to fix things. They've hired you, your company, to bid on supplying the software, and their specification. They're only going to have one voice. They're not going to have multiple people. In the same way that if you wanted to buy a house, you and your significant other would probably work together in figuring out what you wanted rather than each one running to the architect saying, this is my vision, here's my vision. So in general, if you're working for a software company, there's only one idea that's going to match. If you're working on a product that's going to be going to multiple customers, then you're dealing with your marketing department, and then you can get differences of opinion. And in that particular case, if you're the software architect, your job is to say, you're not helping me. You're giving me two separate, depending on what you think this word means, the application is going to do two totally and completely different things. A simple example of that, you're doing a student information system, and the word absence. What is an absence? And an absence in some states can be if the student is 10 minutes late, and in other states, if the student doesn't come in before 10 minutes before the period ends. Your application needs to reflect that difference, and it can be very subtle. And it's the architect that's saying, this is what that word means. Here's how that application needs to be coded.
Okay. Question in the chat from Denver. Okay, I'm not sure I have that correctly. In my experience as a software architect, project managers did not understand the components and couldn't plan well. Do you think project managers should be able to understand system building blocks?
Sure, the emphasis there being on the word should. The problem is many times the gentleman's quite correct. They don't. And so that conversation, the project managers, I'm putting those folks on they span the project. That is, they understand about timeframes and what depends on what, and they're focused on dependencies. But in terms of the technology and things being developed, the architect is the one that has to say, okay, here's the trade-offs on this. You can either spend more money to add more people now, or it's going to take longer to deliver, or it's not going to have all the features you want. And that triangle of how much are you going to spend up front, when is the due date, and what about the features, that's a balancing act. And the project manager has a lot to say about that, but the choices that the project manager is faced with probably can best be vocalized by the software architect. It's part of the job.
So Corvin asked earlier about the sort of differences between the role of architects and program managers, product managers. Could you talk a little bit about sort of the difference or between the role of an architect and a software developer? Where is that boundary?
So that's a good question. And the assumption is that architects know how to program, that they've come up from the programming ranks. An architect who doesn't program is kind of like a priest at a wedding. He enjoys the ceremony, but he can only imagine what comes after. If you're an architect, you have to be able to bridge between the person who's designing the application, whether it's the product manager or whether it's the customer, and the programmers. in the same way that you wouldn't, you could say, how much does a carpenter have to know about, about architecture? And the answer to that is, well, there's that gray area in the middle. The architect produces the blueprints, but then between the blueprints and the carpenter or the plumber stands the general contractor who's saying things like, we're going to use this type of pipe, and we're going to be, and it's going to run from here to here, and it's not going to be lead, it's going to be copper. So the usually on a software project, unless it's a really big one, the architect steps in and does some of the general contracting. In the case of a software application, that could be, um, is what is a security system that we're going to use, which the programmer would maybe not know or wouldn't have that opinion. The architect might decide this is going to be hosted in the cloud or it's going to be hosted in a data center. Maybe we're using this programming language. Maybe. The programmer might have the decision over the programming language. So the interface is really, the architect is translating what the product has to do, what the application has to do based on interaction with the domain expert or the marketing team or whatever. The programmer, obviously, if you've been programming for a while at the company, you're moving into that higher level thing. You're deciding, um, these are some of the decisions are right based on your previous work for the company.
So we have in the chat, Dominique thinks that an architect who cannot code is a runaway situation for the customer and the developer. So opinions. I have a question from Ken Johnson. Okay. Question from Ken Johnson. It seems really important to be able to understand relationships like has and owns. Could you teach us these, what the classic ones are, and the techniques to help us identify these?
The answer is yes. The question is, can I teach you here in a 3-minute answer to a question? Let me give the one big difference between two relationships that's important to know. It's the word has and the word uses. So for example, a student, for example, a student uses a schedule object to figure out whether or not there's a schedule conflict with a section that they want to take. A student has a name, has, has implies that it's visible. Uses is an internal thing that can be changed. So a section, a student uses a schedule, but a section has a schedule. And the difference is the student asks the section for its schedule and then compares it with its own schedule. Now, externally, there's no proof that the user internally is using the same object, and in fact, doesn't have to, because if it's not in the public interface, it by definition can be changed. Whereas a section needs to present its schedule, because in order to figure out whether a room or a teacher or a student can take that section, you need to have that schedule. So uses and has is a very important distinction because it defines the interface. If you don't have to admit to having it, then keep it hidden. And that level of encapsulation means when you extend the application or you're making some changes to the application, the less that everybody knows about the details of another object, the easier it is to make changes because they're invisible to the software that's not directly involved. So that's a big decision in terms of relationships between has and uses. Those are not the relationships in the conceptual class diagram, which are more conceptual relationships. So a student enrolls in multiple sections, and that concept is what the domain expert or the marketing team, that they understand, and so that diagram is visible to them. You get into uses or has, and they start fading off because everything becomes has. Well, a student clearly has a schedule, and the answer is yes, but if it's not visible, that can change. Whereas a section has to have a schedule because we've put that in to the application. So that would be an example of how you would use those standard relationships in laying out an application.
So we only have a couple minutes left, and here's a big question to see what you can do in 2 minutes. Mike Charbazi, which I'm sure I'm mispronouncing, architecting Greenfield's project is clear, but can you address the role when the architect walks into a project that has been hacked together as in an acquired startup?
Okay, actually, there's three, and I didn't think that went to a different place I thought it was going to. Greenfield's project says we're going to put together something that's, that from scratch, and that's the most fun, but typically what an architect faces is the application already exists and it's running at 3 sites, and you want to put it into a fourth site, and that's where it gets ugly because you're trying to integrate this application into an existing system. What you face is, so for example, take the enrollment application. So you have um, one of the things you need to do is you need to get information about a student that your application doesn't have. So for example, to compute the prereqs required for a section, you need to, and see if the student has those, you have to be able to get at the student's transcript. So you're writing an application and you're saying, okay, give me the transcript of this student. That the way you get that could be different at different sites. And so a lot of what you're doing is fitting the application that you already have into the corporate infrastructure at those sites. Could be a data model, there could be a message broker. You might have a different vendor who has their own application programming interface to get that data. And so the architect isn't starting with greenfields. It's not everything new and all the rest of it. You're dealing with an existing enterprise, and you're trying to take your application and fit that in. In the question that was asked, which is how do you deal with something that's cobbled together? There it depends. Typically there's if there's a severe time crunch, you're trying to talk with the developers, bring in the programmers into the system, because again, there you're dealing with, well, we absolutely know what we have to do. Okay, that's been defined, but the way that we're doing it is terrible. And that's a programming problem more than it is an expectation problem on the user's end.
Yeah, you're right. This is a big sort of question that Mike is asking. And I'm going to have to cut you off here, Ron, so we can move on to Juval. But Mike and crew, that question will come up. We have a couple other speakers who will also speak to it. And we also will have Ron here back within the hour. And he can perhaps continue on with some of that answer. So thank you, Ron.
I shall return.
Yeah, you shall return. And so now let me introduce our next presentation. It's Juval Löwy, who's going to be talking about the Zen of architecture. And I just want you to be forewarned that it may not be that Zen, because in this upcoming session, we'll be sweating through the first law of thermodynamics. We'll briefly visit before and after the Big Bang, and we'll touch on the philosopher's stone, that magic substance that can turn common metal into gold and silver. So Juval, please take it away.
Hello, welcome to Silicon Valley Code Campfire. My name is Juval Löwy. We're going to spend the next 20 minutes or so on the Zen of architecture. I will endeavor in this very short session to teach you everything you need to know about architecture and literally to save the rest of your careers. Nothing less will actually do for this session. A few words about myself. I'm a software architect. I'm the founder of a company called iDesign, which I launched 23 years ago, devoted for nothing but software design. I've had some of the most fundamental breakthroughs in modern software engineering of the last few decades. Some of my ideas, like microservices, are obviously household names. I've had several other ideas, including what I'm going to share with you today, which I'm much more proud of. Over the years, we've helped iDesign customers across hundreds of projects deliver great software on their commitments. I published 8 books and more than 100 articles on my ideas and techniques. Before iDesign in the late 90s, I was the chief software architect of a Fortune 100 company in Silicon Valley, and I managed the architecture department. Before that, I was division architect. Before that, just an architect. I'm well into my 4th decade as a software architect. I never worked for Microsoft, but I was privileged to be part of the strategic design effort of key products like C#. Microsoft recognized me as a software legend, something they only gave to 6 people so far, due to the impact they had on the industry over the years. Enough about me, let's talk about this session. What I'd like to show you is the essence of good design, not just software design, but in general design. Unfortunately, if we just start talking about that, it would not make much sense because it is radically different from what you're likely doing now. Now, I'm painting with a broad brush. Maybe here and there somebody's doing it right, but by and large, everybody's doing it wrong. Not just wrong, they're doing it the worst possible way. So we actually have to start first by discussing what not to do. And only once we discuss the what not to do and we nail it to the ground and you say, I can't take it anymore, then we can discuss the what to do. And so by far the most important thing you need to learn is what not to do. And you must avoid functional decomposition. So what does it mean? Architecture is always and everywhere an act of decomposition. You take a big nebulous idea, the system, and you break it down into smaller things. These can be components, modules, subsystems, services, classes. It doesn't matter what it is. It's always an act of decomposition. Functional decomposition is basing the decomposition on the functionality of the system. So if the system needs to do an A or a B or a C, you will have an A feature, a B feature, a C feature. They will have an A block, a B block, a C block. That is functional decomposition, and that is the kiss of death. When you do functional decomposition, the project has already failed, past tense. Before you even write the first line of code, the project has already failed. And yet, this is what everybody is doing. Now, functional decomposition is so bad, I'm going to be throwing you lots of reasons why it's bad. Every one of them is going to be enough to kill it, another nail in the coffin. I will save the best nail in the coffin for last. Only once we discuss the right way of doing things, you will see what functional decomposition is so bad. So let's start with some obvious things. Functional decomposition is always time decomposition because you don't do A, B, C. You do A, and then you do a B, and then you do a C, which means built into the fabric of a B is a notion. It's called after an A and before a C. Suppose you have another system over there that needs to do a B as well, billing, whatever. And suppose the A and the B and the C are invoicing, billing, shipping. Well, you cannot just lift the billing and put it in another system because in the other system, nobody's doing the invoicing before it and the shipping after it. So the moment you lift the B, the A and the C is hanging off it. And now you understand why none of you has ever used anything from anybody else. Nobody has ever done in the history of software, of full design system, the following. Take a business object, something designed for a particular system, lift, shift, drop it in another system. Cannot be done. Which means functional decomposition precludes reuse. And reuse is a fundamental principle of good engineering. Now, a decent system is not going to have just A and B and C, meaning 3 things. It can have 300 things. If you truly do functional decomposition, now you have a design with 300 blocks. Is a design with 300 blocks a good design? We obviously know it's a bad design. Why? Because even if each one of these 300 is straightforward and simple, the integration cost in any system is non-linear to the number of things that you have. It tends to be even hyper exponential because it's according to the factorial of the number of things that you have. So now all of a sudden, a system with hundreds of things is impossible to contend-wise because of the integration complexity. The other extreme is pump and bloat. You take this service and you pump into it the A and the B and the C, and you got these 300 things inside it. Now, while you don't have that much of an integration cost, now you have an explosion of internal complexity. And even if you have just 2 or 3 of these things, they are so abhorrently complex, nobody can reason about it. Sometimes you see these things side by side, few monster God objects, and then an explosion of little things next to them, and nobody can maintain these systems. Another problem with functional decomposition is that somebody has to say to the system, do the A, do the B, do the C. Well, who is that somebody? Well, that somebody is the client of the system, say the web form or the web page or the mobile device. But think about it. What if for that customer over there, we're not doing B, we're doing B prime? And maybe for that customer over there, we're not billing, we're extending credit, so we go and do A and C or whatever. All of these things are business logic. And that business logic now must reside in the client. Every developer this side of Alpha Centauri 2 knows do not pollute the client with business logic. 100% of developers are doing it. They must pollute the client with business logic because of the functional decomposition they have to contend with. The client is the one stitching these things. The problem now is, suppose you have this web page, whatever, and then marketing comes to you and says, let's add a mobile device. Well, is it just adding mobile device? No, it's duplicating the business logic from the web page, putting it in the mobile device, and they're all slightly different. Now I have to maintain the business logic in multiple places. And then they want to have still a desktop and maybe some HoloLens and 3D dimensional. All of a sudden, developers throw the hand in the air and they say, we can't take it anymore. We can't have more clients. But the business wants to have more clients. Another problem with function decomposition is as you enter the system to do the A back, the B back, the C back, you've entered the system in 3 places or maybe 300 places. And that means there's multiple places to worry about security, throughput, availability, responsiveness, performance. Now, we all know a good design should minimize the number of points of entry, ideally just one. But functional decomposition tends to maximize the number of points of entry. I can prove to you that functional decomposition is the wrong way of designing any system without using a single software argument. I'm going to refer to the first law of thermodynamics. The first law of thermodynamics simply states that you cannot add value without sweating. Now, we don't know why this is the first law of thermodynamics, but we know that on this side of the Big Bang, that's the way things are. Before the Big Bang, inside the singularity, maybe the first law of thermodynamics does not hold, but on this side of the Big Bang, that's the way things are. Why? We do not know. In fact, the only way to define the moment of creation is the moment that the first law of thermodynamics kicked in, which basically means you cannot add value without sweating. Why? We do not know. There is nothing in Newtonian physics that mentioned the first law of thermodynamics. It took Lord Kelvin a little bit more than 100 years ago to phrase the first law of thermodynamics. Now, suppose you're doing functional decomposition, and suppose I'm giving a requirement spec for the system. It can be a nice document with 1 is A, 2 is B, or maybe a set of sticky notes on a Kanban board with A and B and C sticky notes. And I say, design me a system. You say, no sweat. A service, B service, C service. And that's the problem. You said no sweat. Now you're trying to cheat the first law of thermodynamics. Now you're saying, on one hand, I'd like to have I'd be a highly paid individual and get a lot of salary. And I'd like to do architecture because architecture is an added value activity. On the other hand, you endeavor to cheat the universe by trying to do it without sweating. And that is simply not going to happen. So here, without using a single software argument, I prove to you that functional decomposition, by the nature of the universe, is precluded from ever working. And yet, that is exactly what everybody is doing. Why? It's the allure of the free lunch. Human beings cannot resist the allure of the free lunch. Now, we all know there is no free lunch in the universe. But functional decomposition, of course, pretends to be free lunch. It's so easy. That's my architecture. Now, because human beings cannot resist the allure of the free lunch, you always do functional decomposition. This, by the way, has nothing to do with intelligence. For thousands of years, the smartest people in any kingdom were the alchemists. The alchemists were trying to convert base metal like lead or nickel to gold. They commanded king ransom. They produced exactly 0 results, and yet for thousands of years, people kept trying. People cannot resist the allure of alchemy, of free lunch. And again, this has nothing to do with intelligence. The greatest alchemist of all time was Isaac Newton. Isaac Newton spent 2 years writing Principia Mathematica, and he spent 22 years trying to figure out the Philosopher's Stone. Your developers are not smarter than Isaac Newton. This has nothing to do with intelligence and everything to do with human nature. Human beings are attracted like moths to a flame to functional decomposition. The correct way of designing any system is to decompose based on volatility. These 4 words, decompose based on volatility, is everything you will ever need to know about any kind of design. The idea here is that you strive as an architect to identify areas of potential change in your system. Those you encapsulate in services, modules, components, and then you implement the required behavior of the system as the interaction between these encapsulated areas of volatility. This is the only way to design, by the way, any system. Everything around you is designed this way. For example, let's talk about pumping blood. Pumping blood is incredibly volatile. High blood pressure, low blood pressure, running, sleeping, with adrenaline, without adrenaline, dehydrated or not. And yet, all of that volatility is encapsulated right here in a component called the heart. If I had to worry about pumping blood right now, I could not deliver this session to you. I can drive your car and you can drive your car. Now, you can drive my car. Now, unless it's a complete clone of each other, there isn't a single reusable component. You cannot reuse my carburetor or component. You cannot reuse my carburetor or my gearbox or anything else. So there's enormous volatility between these 2 cars. However, the reason I can drive your car and you can drive my car is because the volatility is encapsulated. It's encapsulated behind the dashboard and the accelerator pedal and the brake pedal. So in all good systems, we always encapsulate the volatilities. Now, if you were to implement a car, the car has a feature, take you from A to B, but there is nothing in the car that takes you from A to B. You implement the feature of the car by integrating areas of volatility. I'm giving you now this session by integrating areas of volatility. We discussed the heart, but there's also a liver that encapsulated the volatility in metabolism. My laptop encapsulates the volatility of what it means to store the PowerPoint file and also to stream the network. And my internet provider encapsulates the volatility of what it means to connect to the internet, and on and on and on. That is the only way to design anything. The reason this works so well is because when you start using volatility-based decomposition, you envision your system as a series of volts. Every volt encapsulates an area of potential change, a very risky change. Now, when a change happens, it's always a negative thing. It's like a hand grenade. What do? You open up the appropriate volt, toss the hand grenade inside, and close the volt. And the volt does poof. Now, whatever was inside the volt may be completely destroyed, but there's no sharpener flying all over the place, destroying everything else. Put differently, you've contained change. And now we finally understand what is very bad in functional decomposition. In functional decomposition, because you decompose based on functionality, by definition, the change cannot be in any one place. And so now, when a change does happen, it is like swallowing a live hand grenade without the pin. And now when a change happens, it detonates everything and shreds everything. And good system design must be resilient to change. Change is good. Change is what keeps all of us employed. If the world was static, none of us would have a job. We are here because things change, because requirements change, because the world is dynamic. Volatility-based decomposition doesn't resonate with the change, it contains it. Functional decomposition maximizes the impact of the change. All the other things I said about it, that was enough to kill it, like 300 blocks and monster monoliths. But what about this? Now you understand all the horrible things that have happened in your past systems. Now you understand why all of these systems have what you call technical debt, why you cannot introduce changes. All the developers in the universe are bitching and moaning about technical debt. Nobody stops to ask the question, why do we always end up with this technical debt? Was it written in the firmament that we should have technical debt? No, it's because of the nature of the architecture. If you do functional decomposition, you will always suffer from inability to introduce change. Furthermore, something else is happening. If indeed this is your architecture and you can contain changes, that enables you to respond quickly to changes in the business. The ability to respond quickly to changes in the business is the essence of agility. Every developer on the planet said the word agile and agility bazillion times. And yet every developer and architect on the planet has most likely done everything in their power to deny agility. Because when they do functional decomposition, they completely and utterly guarantee the lack of agility. They've maximized the cost of the change. They've maximized the lack of ability to respond quickly to changes. Now, these are universal observations. You will see it when you design an airplane, a house, a laptop, it doesn't matter. But we're not in the business of designing airplanes, we're designing software systems. So you can ask yourself the following question. Are there typical areas of volatility in a typical software system? And if there are typical areas of volatility, are there typical interaction, typical relationships, typical do's and don'ts, typical cardinalities and things to look for? And the answer is absolutely yes. In fact, the hallmark of good architecture that it holds true regardless of context. For example, a mouse and an elephant have the same architecture. Now think how different a mouse and elephant is as far as size. There's nothing in the detail of a mouse and elephant which is the same, and that they have the same architecture. Why? Because there's something very good in that architecture. And so in most business systems, you can identify these overarching architectural concepts. And I've developed a methodology around it. I call it the method. It's a template. It's a mental machinery for identifying areas of volatility. Think of it as a good start point. In a typical software system, you will typically have these areas of volatility. Now your management will vary. Maybe you have more of this and less of that, but it's a good starting point. It also provides good runtime relationship and templates. These things typically do it like this. The first thing to also observe is that good systems are designed in layers. And the reason we like to use layers is because layers layer encapsulation. Each layer encapsulates from the top what happens below. Now, the method gives semantic for the layers and identify what is going on. The top layer, we call it the client. Sometimes you hear the term presentation. I don't like the word presentation because it implies there's a human in the loop and somebody is clicking buttons, and maybe some information is indeed presented, but perhaps this is just an API for another system and there's really no user involved. Ideally, you want to equalize all clients to be the same, meaning regardless of client technology, web page, mobile device, API, they're all clients of your system exactly the same way. Put differently, you both advocate a single point of entry here, but also you allow each client to encapsulate the client technology volatility. So what this layer encapsulates is client volatility. Underneath that, we have the business layer. In the business layer, encapsulate the business volatility. Now, business volatility expresses itself in changes to the requirements. The best way of expressing requirement is use cases. Use cases are simply sequencing of certain activities, and basically they describe the required behavior of the system, not the required functionality of the system, the required behavior. Now, if you're supposed to encapsulate volatility in the use case. What form would that volatility take place? And so it turns out that the business has only two types of volatility. There's sequence volatility and activity volatility. What does it mean? Suppose I have a use case that is doing three activities, A, B, C. Well, how are you going to do this A, B, C? Well, you can do it like this, or like this, or like this. So even though I'm still doing the A and the B and the C, there's enormous volatility in how I'm orchestrating it, in how I'm sequencing it. Since the sequence is so volatile, you need to encapsulate it. The entity that encapsulate business sequence volatility I call managers. Managers tend to implement a family of logically related use cases. What is logically related? That's up to you. You decide what it means. Grosso modo, they tend to map more or less to subsystems. But there's another more subtle volatility in the business. I could keep the sequence, but drastically change the activities. Look at this. These are two identical sequences, but they use different activities. In fact, B can evolve to B prime and then becomes a D and so on when nothing actually changes in the sequence. So the activities can be volatile independently of the sequence. So the other entity in the business is the engine. The engine encapsulates the volatility in business rules and business activities. It's how this customer wants to do this is how that customer wants to do it. Now, because I can always change the sequence without ever changing activities, we said that managers can use 0 or more engines. Engines can be shared between managers. There's nothing wrong with reusing it. Now, underneath that, we have another layer which encapsulates resource access. Now, your system is going to have resources, queues, files, databases, caches, local, remote, cloud. And so there's enormous volatility in how you access a resource. For example, how many ways you have of accessing a database. And unfortunately, none of them is superior to all the other ways. And if it's a local database versus a remote database, I access them very differently. And the way I construct things is very different. So it turns out that accessing a resource is volatile. Now, most people did not miss that point, but what they do is when they try and encapsulate the resource access, they expose CRUDs and IO. So they do select and set delete. That is a really bad idea. The correct resource access does never expose the CRUDs because when you expose the CRUDs, you betray that the underlying resource is a database. If all of a sudden I want to switch to cache, then my select and set delete is toasted and then everybody upstairs detonate. Good resource access exposes the most atomic business context or atomic business verbs. So what does it mean? If use cases are sequencing of activities, those activities can be use cases on their own right, which in turn can be use cases of other activities. And you can keep breaking it like this, but at some point you will discover certain activities which are so atomic, so primitive, there's no way of expressing it in any other business context. So the resource access exposes that. For example, if I have a bank and I have a use case to transfer money between two accounts. So how do I do it? I credit one account and I debit the other. Therefore, transferring money in a bank is not an atomic business operation because I can express it using other operation. But credit and debit are atomic business operation. There's no way of expressing it using anything else in the bank. Now, the beautiful thing about atomic business verbs is that they don't change as long as the business doesn't change its nature. So if you look at banks, since the time of the Medici, banks need credit and debit. And so credit and debit are atomic business operations, as long as the bank is in the banking business. If they move into ballistic missile control, credit and debit are not that useful, but how often does the business change its nature? Not that much. So what you need to identify is those atomic business verbs, and then you expose that on top of the resource access. And the resource access becomes a transformation function between atomic business verbs and actual CRUDs. So now, if you move between database and a cache, only the transformation function inside the resource access changes. Nobody upstairs needs to know about it because they just consume atomic business verbs. And you've encapsulated this volatility. Underneath that, we have the actual resources, the physical queues, the physical databases, and so on. And then we also have utilities, infrastructure, which is common across all systems like security, message bus, pub sub, diagnostic, instrumentation, profiling, those things. So we've got clients at the top, managers, engines, resource access, and to the side, we have all these utilities that everybody needs to use is part of the framework. A good litmus test if something is a utility or not is, can you use it regardless of the business system? You can use it in this system and in a cappuccino machine. The answer is yes, it's a good utility. We're running out of time here, but you can put on top of it a layer of interaction. How do these things typically interact with each other? What are managers allowed to do? Who is allowed to call whom? Can managers call other managers under which conditions? Who is allowed to call down or sideways, and on and on and on. And once you build this mental machinery, the design becomes an unbelievable act, because all of a sudden you encapsulate the volatilities and you have a design that can withstand the test of time. Many times I've put into production systems that were good for decades, plural, decades. 20 plus years later, we will come to it, yeah, design still works, technology comes and goes, the architecture stays. That is the hallmark of a good design. For those who want to learn more about these concepts, let me refer you to my recent book, Writing Software. Note the homophonic, writing, as in standing up correctly. The book has two parts. The first part is about system design, and the second part is about project design. Much as you design the system, you must design the project to build it. And the book marries these two concepts together. You can also find information on the Edison website on the masterclass I conduct. The Architect Masterclass of 2024 is going to be in March next year in California. And with that, thank you so much for your time, and back to you, Peter.
Thank you, Juval, for that presentation.
My pleasure.
You said, and I wish this would be true, that in the first law of thermodynamics, you cannot add value without sweating. So I'm hoping that the inverse is true, that if I'm sweating, I'm adding value. Do you think it might work that way?
No, unfortunately, it doesn't say that if you sweat, you add value. Now, there are lots of people in the world that believe that if they sweat, they add value, but that's a classic mistake of confusing effort with results. Yeah,
that's right.
And also, by the way, the first law of thermodynamics doesn't say you have to sweat just before you add the value. Right? That's probably not a good idea. I mean, you don't fatten the goose the night before Christmas. Anything of value needs years of contemplation, preparation, and hard work, so that by the time you have to add value, do it flawlessly, effortlessly, quickly, cleanly, and so on, right? And that's true with anything. I mean, the 10,000-hour rule is true with anything. It's true with flying a plane or martial art or system design, right? That's how much time is required to train the brain to do something correctly.
Yeah. So you've done work for some really big name firms like Microsoft, Intel, Deloitte, eBay, and you've worked on lots of systems. In your presentation, you gave us an example of volatility decomposition, which is pumping blood. Can you give us an example of that from a software system?
So my point with pumping blood it was to illustrate that all good design encapsulates volatilities. We simply could not operate in the world if we did not encapsulate volatilities. One of the reasons that systems have technical debt is because they did not encapsulate volatilities. And it doesn't matter what the thing that caused the pain could be connection to another source of information, some feed. It could be how they access a database. It could be how they calculate something. If it's not encapsulated and then that thing changes, it's like tossing a hand grenade into the system. So pick anything, pick how you access a database, pick how you calculate something, how you orchestrate something, how you even display information, right? Because UI technologies come and go. So everything that changes, you have to encapsulate. And this is obvious for most people if we talk about, say, properties. Everybody knows, do not expose public member variables, right? Use a property instead, right? Because if there's additional rules on how to access that property, that member variable, like the value cannot be anything between 20, 25, or whatever, and then it changes to include 15. If you expose a public member variable, then everybody has to now change and reflect that. So we all know, no, put that inside the setter and the getter, and now you have it in one place. So everybody understands that when it comes to encapsulating the change to a member variable, you need to have a property. But they completely miss the point that it's exactly the same at the higher level, which is the architecture itself, right? That the very building blocks themselves need to encapsulate volatility. And that goes to another point, which I didn't discuss at all at the presentation because of lack of time, which is you should never design against the requirements. You should never reflect the requirements in the architecture right now. So it's even a level beyond just functional decomposition. And the requirements or the added value is what you provide by integrating these encapsulated areas of volatility. So just like the behavior of an object is the integration of the various pieces inside the object, internal logic, external logic, and so on. So these are universal observations about design.
Makes sense. So we have a question from in the chat from Corvin. What is the relationship or correlation between the volatility of a system and the constraints of a system?
Constraints are actually a good way of allowing the design to emerge faster. So the worst system to ever design is a system that has no constraints. It's like the clean sheet of paper, and it sounds like this. Build me something. What should you do? You figure it out, right? That's the design task from hell, because there's an infinite way of getting it wrong and one way of getting it right. The easiest design problem is a fully constrained problem. Don't do this, do that, never do that. So you don't do this, you don't do that, you do that, you're done. You spend no time on design. Now, real life is neither black or white. Real life is gray. There's some constraints. Some constraints are explicit, some constraints are implicit. Some constraints are stated, but they're actually wrong, right? And so there has to be this preliminary phase where you truly understand the constraints. And you can also impose constraints yourself on the system. So if you could say, we never allow, says a database to call dy. So that's a constraint. It's not written in stone that should never be the case, but you put that constraint on the system. And so the more constraints you put on the system, the easier the design gets. And so since all good designs encapsulating volatilities, by placing additional level of constraints on the system, you enable the design to emerge faster. It doesn't change the end result. You need to encapsulate the volatilities. But what are the volatilities and how do they interact with each other? That can easily be the result of constraints. And in fact, if you read my book, Writing Software, I have a whole chapter called Structure, where so if you think about the act of design as an act of decomposition, that's true in general, but then we can introduce structure on top of that decomposition, and that structure is another way of saying constraints. These components are only allowed to do this, these components are only allowed to call those components. Now, once you introduce that level of constraints, it's another way of accelerating the design effort itself.
Hey, you mentioned your book. Is that where I would go to learn more about these concepts and volatility, decomposition based on volatility?
Yes, it's a very good start. I wrote it for the completely uninitiated. I don't assume any prior knowledge. The only thing that is a prerequisite is an open mind. The ideas are presented in the book challenge the common wisdom and the way of doing things to the core.
Are there any particular tools that facilitate creating architecture based on volatility decomposition?
Not really. It's not a tooling question. You can use any drawing diagramming tool that you like. It's not a tooling. It's a mental shift you have to do in your head of how to approach design and what your design looks like.
And who is using this technique these days?
Virtually every company that you could name has an iDesign trained architect behind the scenes using this technique. And I'm saying it with full confidence. Over the last 20 plus years, I've conducted my architect's masterclass several times a year, both at public events and as a on-site event to companies, and several thousands of the world's best architects have taken that class and are now behind the scenes at literally every company you could name. And we're talking all the brand names, be it Microsoft or Amazon, eBay and such. And hundreds of smaller companies you've never heard about, and startups and everywhere.
So we have Denweir OK, which I'm sure I'm not pronouncing correctly, is asking, what's your opinion on using AI for constructing software systems?
So I have a whole separate discussion on that. And it has to do with a concept called composable design, which is given a set of components that encapsulate certain volatilities, the behavior of the system is merely the combination or the composition of those components. Now, when humans are doing it, humans are not going to sit there and try all possible combinations, because if you have a dozen components, the factorial of 12 is bazillion, so nobody's going to try it. But for a machine, it's called Tuesday afternoon, right? I mean, it's nothing. And that's just a brute force approach. What if you give it constraints, like the previous question? What if you say to it, you're not allowed to do this and always do that? And we know, just from experience, this is a good way of doing something. If you give it these constraints, it's a nonlinear reduction in the number of combinations. In fact, now you can have machines literally running the current system and all proposed design in the background and seeing which one evolves better. And there's already several companies in the Bay Area, where we all reside now, that do just that, meaning they have actually harnessed AI to do this combination. Now, this is not like a code pilot and such, where they just look at all of Stack Overflow and they just guess what the next line of code should be. No, we're talking about using libraries of ready-made code components. Now, it could be modules, services, classes, doesn't matter. But components of ready-made code, and all they deal with is the combination of those components. And there's several such components, several such companies, and they report factors like 1,000 times faster designing and building a system compared to doing it manually.
Yeah, one of the issues with these large language models that are trained on this breadth of information is that information contains mistakes, and that factors into how the large language models create their answers.
That's one of the reasons, and Alan Turing already proved it in 1936, that you can never have a computer that actually codes, that codes well at least. And there's actually another level of, but we're not talking about programming, we're talking about designing a system, which is a whole different problem. The fact that the data is always dirty has to do with another problem, which is it's the hierarchy of knowledge, right? At the very bottom, you have just raw data, which is always dirty. Then on top of that, you have information, which is things that you glean from the data. Then on top of that, you have knowledge, which are the things that you know based on the information. On top of that, you have wisdom, which are the list of things you actually are doing and doing it correctly, right? So humans are very, very good at the top of the pyramid and very poor at the bottom of the pyramid. Machines are very good at the bottom of the pyramid and very poor at the top of the pyramid. Programming is the bottom of the pyramid, design is the top of the pyramid. So it stands to reason that if you base your career on trying to compete with machine and programming things, that's not a good decision. But if you base on machines, your career on trying to leverage machines for architecture, then you're going to do very well. And remember, when I'm saying the machine is doing the combination, I'm not saying the machine is even doing the component. It's just doing the orchestration of things, right? Somebody still needs to decide what are those components, and that's a human level decision.
Right. Denweir OK goes on to ask if you could name some of these AI companies and try to, so that he or others could use them in regular work. He would find that helpful. Are you willing to name these guys? Google it. Okay. What's the search criteria you recommend?
Using AI to design systems, using AI to code is a good first choice.
Thank you. So I take it there's no particular technology needed for this way of architecting? Because you mentioned it's not a tools question. Am I right in understanding that?
Hold on a second, Tammy. Something is wrong with the call.
I can still hear you. Yeah, I can hear you fine.
Okay, then speak up, because I lost the connection to my headset for some reason. Let me try and fix that.
All right, and here we have the logo. So I just was following up on, you said this isn't a tooling kind of question, this decomposition based on volatility. I am asking then, does it also mean it's not dependent on any particular technology? Is that the case?
Correct. It's not, it doesn't matter if you're using Microsoft technology, AWS, cloud, on-premise, which programming language, doesn't matter at all.
Okay. So taking a step back, and you've given a lot of talks to aspiring architects and to current architects. Is there any advice you would give to a developer who wants to become an architect?
So I guess the best advice I can give you is that choosing to be an architect is a strategic decision, not a tactical decision. So life is full of tactical decisions, things like where you live, which company you work for. These are all tactical decisions. You will make surprisingly few strategic decisions in your life. Strategic decisions are what to study, who to marry, whether or not you have kids, those things, right? These are strategic decisions and make surprisingly few of them. Being an architect versus being a developer is a strategic decision. And so you have to know what you're getting into. It's not something, I'll do it for 2 years. No. You have to pivot your whole life to do it correctly. What does it mean to pivot your whole life? So you should have the tactical service, the strategic. So if you live in some small town, there's no good opportunities for being an architect, move. If a company that or the line of business doesn't appreciate architecture, pivot your life so that you could be finding opportunities to do it somewhere else. Look for people that can mentor you. There's a whole set of things you have to do to succeed as an architect. And it takes much more time than becoming a developer. You can literally teach anybody to program in a matter of hours. Teaching somebody how to be an architect is a lifelong pursuit. It's a journey. And so you have to know what you're getting into. You have to seek the right opportunities. You have to find a good mentor. It won't work without a mentor. And probably above anything else, you have to apply critical thinking. Literally everybody out there has their own misguided notion. Everybody think that they know, and you have to basically apply critical thinking. It's not, and it's especially the case with things that are almost intangible, like good design versus bad design. How do you measure it? How do you know it's any good? Well, that's where you apply critical thinking, right? And to do that, you have to develop other muscles in your brain. You have to have a high degree of accountability. You have to have high level of integrity. If many times when you're doing the job of the architect, you're the only one in the world that will know if you messed up or not. Nobody else can tell the difference. And so that's where integrity comes in, right? That's where honesty comes in. And so all of these things are things that make the difference between a great architect and just somebody with a business card.
Thank you. So if I just getting back to the volatility decomposition, if this is kind of a new thinking for me, if I want to learn more about it, should I go to your site? Should I try to contact you? What do you recommend? Should I just Google it? What would you suggest?
You could practically I'm the worldwide advocate of this approach. So look at my work over the years. Start by reading writing software and watch other sessions I have on it on YouTube where you could start. Try and get into one of my master classes. I'm doing it once or twice a year. So we typically have a long waiting list before even the class ever starts. So try and get on one of those lists is a good start. And start thinking about it. Do things correctly would probably be the first step.
Thank you, Juval. It's always a mind-expanding experience to talk to you, and I really appreciate your time and your presentation.
And thank you for hosting this event.
Okay. So now we're going to move on to a presentation by Keith Ball. He's going to take a step back from this sort of critical skill that Juval's been talking about, specifically volatility decomposition, and look more holistically at all the things an architect does. And good news, it's only 5 of them. So we'll also learn in this next section about what you should do if you make a mistake. And at the end, we'll have a chat with Keith showing here about to come in. We'll have a chat with Keith in his mountain house. So let's hear what Keith has to say.
Hi, I'm Keith Ball. I'm going to talk about what successful architects do. These are the 5 things that will be covered in the presentation. Software architects are leaders in their team and the broader organization. Of course, they're experts in their technology, the development and deployment of their solutions that they're working on. They need to understand their business needs and build the solution for it. And as a leader in the organization, trust is the foundation of being successful as an architect. I was an architect, software architect for over 20 years, many of those years in the media technology and services business. My last job was at TiVo. I was there 11 years, and at the last few years, I was a distinguished engineer, but I'm retired now. The first area that I want to cover is knowing your system. You need to understand all the components of the system, the solution at hand that makes your product, and how they work and how they fit together. Now, you need to cover this not at the code level, which you need to know, of course, for some aspects of it, but from an abstraction from the code so that you can get a sense of how all the pieces are put together and how they fit without actually getting lost in the weeds. To do this, you should document what you learn about the system, what you understand about the system, not only so that you can get a deeper understanding, because I always feel that when you're creating a document, you understand it better, but as well as a basis for explaining to other people. It's important that not only that you understand, but the team and the broader audience, including the management of the organization, they need to understand how the system works, how it fits with the business needs or doesn't fit with the business needs, and how things need to change so that when the business needs change or as the business needs evolve, what you need to do to make the system fit and work again. So that documentation, it fits whatever form it works for you and also whatever works for your organization. You have to be culturally sensitive to how your organization works and know what documentation works best. As the business needs change or evolve, you're going to need to explain and adapt your understanding, and also adapt your explanations to how that system has to change and what things are expensive or not expensive to put into the system, and what you're going to build and what you're going to partner with. And then, of course, the very important part, fundamental to building trust within your organization, certainly with the management team, is you need to justify why you're doing this. You need to explain to people why the system as is or the system as it needs to change will solve the business needs at hand. Next, it's important to lead and support the engineering team. It's not just that you need to work with the developers. You need to empower the developers. You need to make sure that they are effective with their ideas and with their actions. So first thing is you got to always value their opinions, and you don't value their opinions just by internalizing them. You need to be valuing their opinions by being actively supportive of their ideas. They need to get that. You need to have that feedback loop present so that they understand what they're saying and how you're internalizing it and expressing it to them, giving them that feedback loop, but also that when a person, who won't speak up or somebody who is not actively participating, you bring them into the conversation in a way that's effective for them. And then they hear that you're saying, they see that you're valuing what you're doing by bringing them into that discussion. Second, if there's a person who is like not being heard, but has valuable opinion, speak up for them and tell the group that, hey, this person here is saying something that's really important and valuable. You guys need to listen to what that person is saying. And then as you're working and understanding the system and the changes you want to put into the system or whatever other aspects of work that you're doing as the architect with them, and reflect that feedback into your work, and so that they can see that you're really listening to them. Then, of course, all architects have to ensure that the right infrastructure and development tools are present in the organization so that the team can be effective and productive. So the architect needs to lead on this. They need to create and build, deploy, develop whatever tools and operational infrastructure is necessary and have it operating and working effectively for the system. But you need to also show people how to use it and validate that what you want to do is going to work for the system that you have and the requirements that you have from your business. So one of the things that's important to do is to design and to create design patterns that show how to effectively use the tools and infrastructure that you've put in place, and document these so that other people can utilize those patterns in their work. And then, very importantly, you need to build examples. These examples show somebody how to use the infrastructure and follow the design patterns. And it also allows you to validate and test the infrastructure to show that it'll work reliably and effectively. A better example would to actually build a real component, a component that will be part of the end solution, and have that thing operating in the system based on your new design patterns, your new infrastructure and tools. And this really establishes to your team that this infrastructure is in place, that you're fully behind it, and that you're there to help them to understand how to do it. This is very important aspect of the trust that you have to build with your team, is validating that infrastructure and ensuring that they understand how to use it. Then probably even beforehand or while you're doing it, you need to evangelize that infrastructures and tools that you build. And not only do you need to evangelize it to the engineering team, you need to evangelize it and justify it to the management team as well. Remember, they're going to be the ones with the budget. They're going to be the ones who are allowing you to spend money to build and develop something. So you need to make sure that they understand what you're building, why you're building it, and how it's going to really help build a better solution all around. And then lastly, gets back to how the team works and how to be really a leader in the team. As you see the team do something and do something successfully, make sure that you're out there giving credit for the team. Tell people what's going on, tell people what they did well, and tell people how you really appreciate the hard work that they've done and the success that they have in the building of that function. And lastly, if things go wrong, if you make the mistake, own up for your mistakes. Make sure no one else is taking the blame for you. You need to be the leader. And if there's blame that needs to be apportioned, you should accept and take that blame. Even if it's the team making a mistake, you take that blame for them. This is going to show them that you have their back. They're gonna appreciate you standing up for them with the team. Remember, you built your support with the management people. Now this is going to leverage that support in building more of that foundation trust with the team. So building and supporting your role, you got to listen. Listen is probably the most important thing. Don't just keep out there evangelizing your ideas, talking what's important to do, telling people what's important to do. It's okay to do those things, but make sure you listen to your management team, your engineering development team, the product teams, whatever organizational things that are involved in the solution that you're building. Make sure you're listening to those people, and then make sure that when everyone talks and has an idea, that everyone's idea is heard. Like, take ownership of making sure the communication around the group and people involved in the solution and the architecture is heard, and then empower those people on your team and in other organizations to lead. Make sure that the product team is, that their leadership is being respected and understood as well. Lastly, the importance of trust in management and what is often around delivering to your promises. So tell people what you're doing and make sure you do it. If there's issues, make sure you tell people about the issues. Manage up. Make sure that you're driving the management of what help you need, and when issues come up, what issues are coming up, and if something needs to change, why you're changing it, and what needs to change to go along with that. So, not only tell them what you're doing, but tell them also what you're not doing. And then listen to the management, listen to the engineering, listen to the other aspects of the organization that support the development and creation of the service and solutions that you're building. Listen to that and then incorporate that into what you are doing as well. Take that feedback and show that you're listening to them and valuing their opinions. And when there's something that you disagree with, be upfront about it and be clear about it. Don't be judgmental. Don't, just explain why you think that what you need to do is this versus what somebody may be suggesting. So you need to find your replacement. And I don't mean that in terms of you need to cast yourself out of the organization. The idea is that you're finite. Everybody is. You can only do so much. And the list of work for you in your organization is going to be beyond your ability, beyond anybody's ability. A successful organization is moving forward and wanting to do more and more and more work, and you're just not going to be able to keep up to do everything you want. So for sure, you need to be able to prioritize your work, and you need to be able to be clear on what you're doing. So what I do is I've made a list of 20 things. I pick the top 5 things that I'm going to work on and make some accomplishment in some time period that I'm discussing. Could be a quarter, could be whatever the time frame is appropriate for it. And then I'm going to pick the 5 things that are on the bottom that I'm not going to do. They're going to get no attention. They're important, but they're not going to get any attention. Then I'm going to take that list of 20 things. I'm going to ask, what other things am I missing? What things do you think I should be doing that I'm not doing? And, if somebody wants to, if somebody's telling you need to do 10 things, I always said, no, this is all I can do. I can do these 5. I can do 5 things. You can change the 5 things, but you can't, that's my capacity. So you need to make sure people understand that you have finite capacity, but then take their feedback, integrate it in, come back with your updated list of things, what you prioritize and what you're doing, what you're not doing. And really, it's important to build trust on this thing by doing what you say you're going to do, and people hearing that you've taken their feedback. But it's really important that you need to justify, especially the 5 things that are not getting done. Why are these things less important or not important versus the other things that may get some attention and the things that will get most of your attention? And then, now this is the aspect of replacement, where I meant replacement, is you need to find individuals on the team or beyond the team, whatever within your organization. I mean, even if it's somebody outside, maybe bring people in, but at least within your organization that you feel have the basis, the capabilities of being an architect, a software architect. That they may not be there already, they may not even be close to being there, but they have the foundation in them that will be an architect. And then take those people and mentor and guide them. So some people may be relatively close, and mentoring them, guide them may mean getting them an architecture project that either you're doing or one of the ones that you're not doing, and have them do that project and help them with that project. Make sure that they do a good job with that project, and make sure whatever areas that they're working with or struggling with, that you're there for them to help them, show them what to do, make sure that they understand what it is. And then and very importantly, make sure the management teams understands why you're doing this with them. Make sure that their objectives are tied into this thing as well. That's what you really want, because, I'm assuming these people want to be software architects. So you're going to need to give that management team a clear idea that, this person has this feedback for you, and you need to talk to them about setting their objectives and giving them the capacity and space to do this. Because you just can't pick somebody out of the organization and start changing the work that they're doing. You're going to need to evolve this with the management team. But still, the mentoring and the guiding them is really independent of them actually doing a project. That's where it has to take the more coordination. Mentoring and guiding them and showing them what a real software architect's going to do and how it's going to work, that you can do on your own with just working with that individual. And then, over time, you'll see how they're working. And then at some point, you're going to want to talk to that management team and say, hey, look, this person is really coming along here. We really need to give them a chance to improve and get better, and maybe take on some of these responsibilities that we have hanging around that aren't getting done. And then once you get this person up and running and doing some of this project, you've basically just stretched out your ability to do more work. You're basically leveraging all this other people in the organization to get your big priorities of architecture done. Things that you couldn't have done on your own because there's just not enough of you to go around. Now you're actually succeeding and getting those things done because you've actually went out and made you more effective, made yourself more effective by leveraging more people. So I just want to give one example here of something that I did that, started out not working out so well and ended up working better. So I was new to a company, and I was learning. They have a pretty good size back-end service system, and had a lot of components and millions and millions and millions of lines of code, and old pieces and new pieces. And there was people that had expertise in different parts of it. And so I was going around and interviewing people and discussing how things worked, and then building different documents about covering the different subcomponents of that service, configuration management, for example, or provisioning, or whatever aspects of the system, the application specific functions. And as was my nature to do things, which I had done in previous organizations I created a narrative document with some pictures in it and a description of how the components were and what all the pieces were and how it all fit together. And when I got, to a suitable level of accomplishment in that document, I started, sending it out in a normal way to people and to read and to give some feedback or ask questions about it. It wasn't, it was a small set of people that were able to give me these feedbacks on these documents, but I just didn't get anybody to give me these feedback and or questions. And I know, if nobody's giving you feedback, if no one tells you your idea is a stupid idea once in a while, then no one's listening. So I didn't get any of that feedback. So I said, oh, this is not working. So I decided I needed to take a different approach. So I started to build diagrams of the major systems and the subsystems. And I started breaking those diagrams out into more detailed types of diagrams. I liked using UML modeling, which I was very into back at that time. And I built UML models, different types of them, and do that. And I built an internal website with all the diagrams, and I published them on there. And then I had small groups of people, 4 or 5, and I made presentations to those people. And I used the diagrams and talked with him, and then I started getting a lot more feedback, a lot more interest in what I was doing, a lot more questions, a lot more people saying, no, that's not exactly how it works. And of course, then I improved my understanding considerably, as well as now we have this document of this abstraction of the whole system. I believe we improved the whole knowledge of the organizations of the system. So the key thing here was I listened to feedback, or frankly, I listened to the lack of feedback, and then I changed my direction and found something that was more culturally compatible with the organization and the people that I was working with, and found that I had a better solution, and evolved and developed that solution over many years, and actually got other people in the organization and other senior architecture people in the organization to adopt this tool set. And it became a standard in a lot of the things that we were doing going forward. Well, that's all I have to say in the presentation. Thank you very much. I hope you got some value out of this. Bye.
Well, thank you, Keith, for that presentation and for joining us from your mountain house there. I gather it's kind of cold and rainy.
Not too cold, but rainy.
Couple questions from the chat. We have John David Duncan. In the smallest projects, the architect writes tests and the developer makes them pass. Can you describe the relationship between the architect and test developers in a larger organization?
Test developers. I don't know. I don't see why that's any different than any other developer that you were working with. You're going to provide guidance and support for them like you would any other developer. It doesn't seem to be different than I would with somebody developing the code for the product. Of course, the subject matter is different, and large organizations. None of the organizations I ever worked with were large enough for this, but large organizations can also have architects that work on the test development systems and the test systems. We had test infrastructure in a couple companies I worked with, and we had people working on them, but often the architects overall were in charge of what those things were looking like. So those developers needed support from that architect like they would from the architect for like the developers working on the code of the product.
Okay. Corvin asks, what are the metrics an architect uses to gauge their effectiveness as an architect in the organization? Metrics you use to gauge effectiveness.
Well, there probably are some. I just wasn't a person that used metrics to gauge that. So I don't have that information. I just wasn't measuring my performance in that way. We were measuring it in more qualitative issues associated with effectiveness of the project, whether people were satisfied from a management perspective of whether they were getting the support they needed, those kind of things. I didn't have quantitative metrics that were measuring my performance, or any of the other architects I worked with. We just weren't sophisticated enough for that.
Okay. So you explained when you prioritize your work, you have this list of 20 things and you do the top 5 and you tell everybody these are the bottom 5 I'm not going to do. But what about those 10 in the middle? It sort of sounds like you're really doing 15 things.
Well, yes and no. So the 5 things on the bottom are the ones for sure that you are not going to do. And often the importance of those things, they can be very important things. And so you just need to be very clear. And I just picked those bottom 5. It could have been 10 or all those bottom 15 that weren't going to get any attention whatsoever. But the bottom 5 for sure weren't going to get any attention. But sometimes, that depends on those top 5 items. You may have done some work. You may have some capacity to look at other things. And depending on the nature of projects going on, you would do something. You would, like, there could have been a development team. Like when I was the distinguished engineer, I wasn't usually responsible for one project. There once in a while I just had multiple projects that I was working on. So like one of the projects wouldn't get very much attention from me, but maybe the architect that's working for that specific project, I would talk to that person periodically and make sure things were okay. And they would ask me questions. And so they got some attention, but they weren't getting the level of attention, the top 5 things that I were doing. So it's just showing that, these are pretty loose. That the situation depends on how much they're going to get. It could be that you would say, instead of 5, I would say that the bottom 10 aren't going to get any attention because I just know how busy I was.
Right. So some of the lessons I've learned have come from things which didn't go well, certainly not as I had planned. You mentioned mistakes. I'm sure you must have had some of them. Is there something you can tell about how you've learned from mistakes in the past?
Oh, yeah. I've had some significant mistakes in 20 plus years of architecture work. There have been minor mistakes, of course, but there were some really bad ones that I still have bad dreams about. There was one where I decided I wanted to use a new software infrastructure component, an operating infrastructure. It was an enterprise service bus. I had been looking at enterprise service bus for several years and thinking about how to use it and how it would be effective in the environment we were working in. And I knew we needed to change things because we were changing a lot of components with very specific integration projects for large customers. And we needed to be able to switch over. And I was hoping the ESB, which is integration oriented, would help us make this switch faster and make things better. So in the projects that were heavily integration oriented, there were 2 that I started out with, but the projects I did that, I really wanted to try to use it. Unfortunately, the ESB transition went very badly. There were many failures in this. There's the one main one that came across, I'll talk about, was there was the engineering team just was very strongly resistant, and I knew there was going to be a lot of cultural resistance because the development model was very different, but I didn't do one of the core things that I said was the most important thing, which is to establish how you use that development environment. And so I wasn't able to counter that the resistance with actually having examples and maybe some portion of the componentry that was necessary for these key things built out to validate and prove and actually show them how to do it. I was thinly stretched at this time. I was working on multiple large-scale projects for very, very large customers that we had, as doing some solution architecture, which was necessary in the company at the time, as well as doing software development oversight on a couple of internal projects to build core components. And it was just, I was overwhelmed. And the team was, I didn't realize it at the time, was stretched thin as well, too thin to adopt a new thing and lead on it. And the architect that was specific for that project who was leading the details of that project, wasn't able to do the things that I was doing. And not in terms of capabilities, but in terms of just capacity. So to say the least, the project didn't go very well. The adoption didn't go very well. The integration didn't go well. There were some things about the partner infrastructure that I missed that became issues as well in the operating environment because I didn't do enough of that step forward. So the step up to look at how it would work in our operating environment. So quite a few mistakes there. So the key thing I learned from it was, so the really important thing that I got out of that, which is, I guess there were two, which is understand the capacity of yourself and the team that you're working with, and don't make assumptions that new things can change when the level of burden on those people are so high that they just don't have time to make a switch, which was what I was requiring it. And I didn't have time to put in place beforehand the things necessary to make that switch even viable. So, and then the other thing is you got to listen at some point on the team, I think I could have made the decision to say, no, don't use it, use the old infrastructure and pull this out. And if I would have I had to pay attention to what was going on in the project as well as what the engineers were saying. It's like this the getting the feedback and being sensitive to the feedback. It's like I just wasn't listening well. I didn't hear, they weren't like telling me what the problems were in the way that was important. They were telling me what they didn't like about the solution. And that wasn't, of course they didn't like the solution because it was making them change the way they think about it, and they just weren't ready to think about it in a different way. So, but I wasn't hearing that one bit of evidence that's saying, look, we just can't absorb this. And that I learned from that quite a bit to be much more sensitive to those kind of issues. Like,
listening is a skill.
Huh?
Right. Yeah. Listening is a real skill. I mean,
and listening is
listening.
For me, it's like I have a tendency to talk more than listen. It's just my nature. And so I'm always having to have the little voice in my head sitting there monitoring me, telling me all the time that I need to be listening to something, that I'm talking too much. And that's me. I mean, other people, I have people I've worked with for years that are great listeners. You're a great listener, I think. So yeah, I just learned that, when I get busy and I'm under pressure, that little voice in my head wasn't loud enough. And I had to be much more cognizant of that fact.
Yeah, makes sense. We'll have a question from our audience. This is Denware Okay.
Well, I'm sorry?
Which the name, I think, is Denware Okay. We're just
that's the person's name. I'm sorry.
That's the person, yes. And then the question
I thought that was the question. Sorry.
When the system grows in size, in many cases, it is split between multiple architects. The knowledge of the original whole system architecture can start to be missing. How do you deal with that? Oh,
that's a very difficult problem. I appreciate that question. It's really a core issue and gets back to the importance of spending enough time as an architect that documents it. So it's not just you, but it's also the rest of the other architects on the team. And not every architect is interested or has the level of capability. So like I was on a team, we had 3 distinguished engineers that were in charge of the service. And then we had underneath those things, we had a set of architects. So we had a lot of senior people there. And so I it was my nature to want to do this documentation. And so I worked with the other people, and they did documentation too. And we did get a lot out of it across all of us. And we put all that together. And that's how we kept understanding the system. But we found that there were pieces of the system that were like, oh my gosh, that service had been running for almost 15, 18 years. So there was code in there that I didn't even, there was code in there that was written in Tickle. I didn't even know Tickle. It's like, I don't even know if I ever heard the language before I went to the company. And so we had one software engineer that knew Tickle well enough and that was always doing the fixes in that old part of the code or any enhancements we had. So I had to sit down with that person and document enough things and learn enough about it so that we could actually understand at a high level how it fit into the architecture and worked on things. So some of that stuff was pretty difficult. I did also go into one piece of the system that had very complex implementation that was old that no one touched. It worked very reliably, but I had to go and find out how it worked. And especially when we were like thinking about working in that area where this thing was involved, and we had to understand the output of that software. And I had to go through the code. And so it's very important to make sure that that documentation is built, that you continue to work on it, that you don't forget that if you make sure that it's covered, that you talk with the other architects, that they're talking and they're making sure that the documentation for the system is kept up to speed. And then again, of course, you have to spend the time with the project team or teams, making sure that they understand how you abstracted the system and how it works and how it fits together, how their components working with those other things. So it doesn't, the ongoing explanation of the system has to continue as well. It's a very expensive part of the architecture work, I think, but so important to keep the team up to speed and understanding how their work fits in with the rest. And then if you start re-architecting like the system infrastructure, and you're going to have to start upgrading things and moving things around, it becomes even more important that that documentation is up to speed. So the people that are working with that know what's changing and how the things that aren't changing, or at least aren't changing right away, or maybe never will change, how those things fit in with the new components as well. So this is that's even real critical. The maintenance of legacy code.
Legacy.
Yeah, I'm sorry. Legacy code fits into that new architecture going forward, and having that documentation that explains how it works and how it fits in, but also being able to work with those teams about that integration. So it's crucial aspect, crucial question. Really good question.
We all have this mental block. Legacy code, no.
Yeah, legacy code is it's key part of what architecture work. What I used to call figuring it all out, software archaeology.
Yeah. So last question briefly. You talked about the 5 things an architect needs to do. And right now you're talking about know the system, all the parts of know the system. There's also lead the team, build support for architecture across the organization, mentoring and building trust. How do you see your time or architect's time being divided between these sort of 5 essential things? Is it evenly split? I mean, what's your thought?
Well, unfortunately, I don't think there's a pat answer. I don't think I can say it's 20% or this is more important or that's more important. It not only does it vary based on the individual architect and what their skill sets are and what their capabilities are and how well they're able to do things. You have to learn, like you may be good at 2 of those things and not as good as at another thing. And you need to be able to give yourself time to improve your skill sets and learn how to do things. So you may be spending more time on something because you need to develop your own skill set in something. So that's one area that could vary. Second, your organization has different needs. I mean, if there's a lot of a high level of trajectory of change, in the system, you may be spending a lot of time knowing the system, designing the system, and building operating infrastructure and development tools because of that change. And you may be focusing more on that than, let's say, mentoring and finding a replacement for yourself in that kind of area. So it's hard to say what you're going to put time on and when you're going to put that time on. It's very situational on the team, to the set of work over time and what work you're actually working on, the individual architect and what you have to do and what you have to learn about and what you need to work on. And the combination of how depends on the organizational size, the number of architects you're working with, and how much they're going to do, and really working with that team of architects and making sure that the coverage of what you need to get done is being done. Like, don't if you're on a team of architects, communicate. Even if the team is virtual, think of it as a team and bring yourself together with that team and make sure that the things that the organization needs covered are getting covered. I had close collaboration with 4 other very senior architecture engineering people, and we would talk about what we're doing and who's doing what and dividing things up and going to management meetings and talking with senior management about what we were doing and what we knew needed to change. Coordination is very important too. Depending on the size of your organization.
Yeah, of course, makes sense. Well, thank you, Keith. Really appreciated your presentation and your insights here. We're now going to move to our final presentation. We're going to bring back Ron Kleinman and pick up the enrollment system where we left off. That's a student enrollment system at the college. And remember, we had departments and teachers and rooms and courses. And remember, in our model, courses had multiple sections, right? So if a course is offered in the spring and the fall, it would be the spring session of the course and the fall section of the course. We're also going to find out who the Gang of 4 are. So Ron, please wrap it up for us.
Hi, we're back. I hope the previous sessions were informative. We're going to conclude this particular analysis or design of the enrollment system. We're going to dive a little deeper into how the software architect puts together an application. And again, we're only at the beginning of this. This is just what you do at the beginning when you're trying to establish the application vocabulary. We're going to look at a further drill down into what that application vocabulary is for the enrollment system. And we're going to introduce the use of design patterns, which are ways of reusing thinking in the same way that software libraries are ways of reusing code. So we'll continue. We left off with the what's called a conceptual class diagram. It's a UML artifact that shows an overall layout of the way different objects that support the application interconnect. So let's look in particular at what those relationships are. There's 4 of them. When you look at the diagram, you see one college has n departments. N departments belong to one college. That's a one-to-one relationship. There are relationships like one-to-one, where a teacher has a schedule. One teacher has one schedule. The rest of them, for the most part, are one-to-n. So let's look at what that really means. If you're defining, and these examples are going to be C++, which is the bad news, but the good news, they're about 2 lines long, so they should be interpretable. A one-to-one relationship. Class teacher has a schedule. And that's it. It's one teacher, one schedule. One-to-one, one-to-n, is every teacher can teach many sections, but a section only has one teacher. So from the teacher's point of view, it's a collection. In this particular case, it's a collection of 20 section pointers. So 1 to n involves a collection. The 1 collects the n. N to 1 is the reverse. If you have n teachers belonging to a given department, each teacher has a pointer back to the department. So a department has a collection of teachers, that's 1 to n, and teachers have a single department, that's a pointer back. That's the n to 1 relationship. And then you come to the fourth one, which is usually a problem, and that's n to n. A student may be enrolled in many sections, but every section can have many students. So that's an n to n relationship. And those are tricky. Let's take a look why. So we have a student taking n sections, section being taken by n students. How do we implement this? How do you implement an end-to-end relationship? Well, you might try 2 separate pointer arrays. So a student has an array of pointers, 1 to each section. Section has an array of pointers, 1 to each student. And this might work, except for the fact that it has its own data. So a student in a section has final grade, attendance records, exam grades, teachers' comments. Those are all specific to one student in one section. And the question is, where is this info stored? If a student has pointers to a section has pointers to a student, there's no place to store the data that uniquely binds that student to the section. In general, an end-to-end relationship with data associated with it is usually a design error. So what do? You use a design pattern. And a design pattern that we're going to use in this particular instance is the junction class. A design pattern is known to software architects, and this is one of the common design patterns that is used in dealing with this particular type of architectural problem. So you create in the middle between student and section, you create a thing. And that thing, a student collects n of them, and a section collects n of them. And that thing contains the final grade, the attendance records, all of the information that was at that junction between student and section, and it contains a pointer back, being a 1 to n, being an n1 relationship with student and section. It contains pointers to both of them. So if I was the student and I wanted to find out all the sections that I took and what my grades were, I would go and look at each thing that I collected, and that thing would have the grade and would have a pointer to the section so I could get it. And likewise, if I was the section and I wanted to find out all the students in that section, I would go to my collection of things and ask the thing, give me your student. And I could walk through the list of students, and I would be able to get at the information stored in one place about how that student did in that section. The question is, what is this thing? I mean, is it a schedule? Is it a transcript, roster, registration? Some of those, none of those actually fit. A student schedule is something totally different. A transcript is the collection of grades that a student got. It's not one specific grade for a section. It's not the roster. A roster is a collection of students within a section. It's not one student in a section. So we have the concept of the thing, we just don't know what the thing is. So we start thinking, because we're software architects, we think, what binds one student to one section? Well, a student has multiple things. A section is allocated with, in the case of typical section at the end of 55 things. It has room for 55 students, 15 of them waitlisted. A thing is either valid or invalid, whether there's a student there or not. And it contains grade, attendance records, and so on. Calling it an enrollment, you could say, okay, a student has 5 enrollments, one in each section. A section has 50 enrollments, each one by a student. It kind of fits, but if in thinking about it, turns out we can do better. Call it a seat. And the moment we call it a seat, everything clicks. The registrar knows what a seat is. A student has multiple seats, one in each section. A section is allocated with room for 55 seats, some of which can be occupied, some of which are empty. We use the word seat as the thing that binds a student to a section, but notice it's not seat like you define in an airline, where the seat would have a unique ID like seat 44A, and have a unique cost and have an assigned student. A student sits in a seat, but a seat is in the enrollment application is an abstraction. It's not a physical reality. But the moment that you define the word seat to be the thing that joins student to section, everything makes sense. A student occupies n seats, a section contains n seats, and a seat has all of the information about grade, attendance record, and so on. So we've added seat. And at this point, we are starting to really get a handle on what are the refined abstractions in the enrollment system, starting with the functional on what are the refined abstractions in the enrollment system, starting with the functional specification, and then doing some staring at the ceiling and coming up with the first really UML artifact, which is the conceptual class diagram, that's going to define the way the abstractions that we've identified relate, and it's going to define the meaning of these words within the application. So this is what the enrollment system specification looks like at De Anza, after the software architect has corrected it. So notice the highlighted words. First paragraph is pretty much the same. Second paragraph, each course is instantiated by one or more sections. That's important. That's a requirement that the registrar would agree with, and it's a requirement is trying to define, and between what the programmers understand that they have to do. We've added each section is assigned a section number and has a schedule which defines the set of times that it meets. We've talked about teacher and room. We knew that from the beginning. Students may then enroll in a section if they are paid up, have taken all its required prereqs. So we understand that prereq is now a part of the functional specification. And then at the bottom, if the student is accepted, she will be assigned a seat. Her attendance will be tracked. And at the end of the academic quarter, she will receive a final grade. So we've taken the functional specification and we've added to it the things that we needed to do to make that specification real and implementable. And all of this is heading toward defining a common application-specific vocabulary. The software architect is bridging the gap between the domain expert and the programmer. One simple way to do this is, and again, this is just a very simple first pass attempt to define an application vocabulary. If it's a noun, it's a class or an abstraction. If it's a verb, it's a method or a function or a subroutine on that class. If it's an adjective, it's a type. So let's see, virtual section. Well, let's look at an example. A foreign student enrolls in a virtual section. We're going to parse that sentence. This is something that the registrar might say. And in terms of parsing that sentence, we now understand what that sentence means to the abstractions that we've defined. Student is a class. Foreign is a type of student. It might be a child class of that student, or it might just be type of that student class. Section is a class. Those are nouns. Virtual is a type of a section. I have a virtual section. I have an on-campus section. Enroll is a public method. So a student enrolls in a section, or a section enrolls a student. But we understand that enroll is going to be a method that we're going to have to support in one of those two objects. And so when we hear words about the application, we're able to map that to the definitions of the classes, of the types of classes, and of the events or the methods that they have to support. That's what we're trying to do, to take that functional specification and make it into something that can be implemented. I wanted to talk for a minute about design patterns. Design patterns, as we said, we looked at one, the junction set. It took a problem that we had, which was an end-to-end relationship that had its own data. And when an architect encounters something like that in the design, where you go, I have this problem and I don't quite know how to model it, typically what the architect wants to think of is, am I the first architect who ever before ran into this problem? Am I the first one to ever encounter this? And if the chances are no, you're not, then you start hunting for a design pattern. How do I reuse the thinking of those architects that have gone before me? Again, in the same way that a software developer would look for an object library solution to, say, schedule. Why do I want to write the schedule object when it's probably been written already? So design patterns formally document these designs so that they can be reused. And the classic book on design patterns, the thing that created it, is the URL is shown here. This is a PDF file. It's free. It's on the web, and it can be downloaded. It is design patterns. The four authors are called the Gang of Four. That's not to be confused with the people that took over after Mao died in China. This Gang of Four gave us design patterns. And it's worthwhile looking at. As a software architect, you don't have to know all the design patterns in that book, but you do really want to get familiar with the index to the book. So you can look through the index and say, is there something in here that can meet the challenge that I'm facing in this design? So here's a challenge. Policy customization. We have an enrollment system. We've architected it, designed it, and implemented it. And it is running at the Answer College. And we want to sell it to other community colleges. We want to sell it to other training institutions, perhaps corporate training institutions. We want to be able to resell it, but we have a problem. There's a lot of policy hardwired into the application. Policy is things that define how an application works at a given site. So what's the maximum number of credits a student can take in a given term? Maximum number of office hours, minimum number of enrolled students below which the section gets canceled. These are numbers that are part of the application, but they're going to vary with every place that application is installed. So if we're a customer, how do we avoid minimizing the recoding that's involved when we sell it to a new college? Where do we make those changes? We certainly don't want to make them in the code itself, because if we make the changes in the code, that means every new site we sell to has to be recompiled. And that is a nightmare, because it means that we need a separate code tree for each customer that we have, which has their policy constants in. And when we did a fix, we'd have to put it in all those code trees. When we did an enhancement, we'd have to put it in all those code trees. What we really want is one code tree, and to somehow take out of the code all of these specific policy values that are would otherwise be in the code. It has been said, and I'm a believer in it, that the only numbers you ever should see in code are 0 and 1. And if there are any other numbers in the code, it's the page number of the code listing that you're looking at. So how do we get it out of there? And at this point, we might think, well, I couldn't be the first software architect to have to try to figure out how to remove the impact of the various policy values on a given site. So this is the fixed property design pattern. This is the one that we'll use to solve this. And this is how design patterns are defined. There's name, classification, intent, minimize changes by encapsulating site policies. When do you use it? When you use it when business constants are site specific, and that they change on a regular basis. The implementation, you have when in doubt, encapsulate. So we know we've got a problem with taking all those constants out of all of the places that they are in the software. And so what we immediately think of as an architect is, what if we had a solution? Let's define a solution. Let's make it into an object, and let's try to figure out what the interface looks like to that object. When we do that, we realize, well, if we had an object that you would give a key, you'd say, what's the value of this? And you get back a value, that'd be great. I have no idea how I'm going to do that, but I know that if I'm going to do that, that would be the object that would help me pull all of those numbers out of the code. This object would know the numbers. You could ask it, what's the value of this? And you get back the value of that particular parameter at that particular site. It would be different per site, but the code that asked for the value would be identical. It's just this fixed property design pattern object that would be different, or maybe not. You have to look a little further. So here is how we encapsulate site policy. We have key, which is the string that defines the policy. And this would be for a library, for example. Maximum number of days a book is on loan, fines per day, how many months does a library card go before it expires? What's a site license? All of those, we define all of the parameters, and then that's the key. And we ask the site policy object, hey, for this particular site, what's the maximum number of days on loan? Or how many credits can a student take if it's the enrollment system, or whatever the parameter is. The site policy object uses a hash table. And again, I'm not going to get into what a hash table is, but it is a data structure that if you give it a key, it immediately returns a value. And in this particular case, we're looking at a library system, or whatever the name of the application is. Any object in that application relying on a site-specific policy may get the value by going to the site policy object. No code needs to change when the application is run at a new site. Now, the point I wanted to make before I get into the last slide is, how does the site policy object do it? And there are several ways that it can do it. The first way is to just, when you ship your code to a given site, you have a table, there's a file, it's called a configuration file. And the site policy object is the only object in your application that knows where that file is and knows to go there and get the values of those policy fields for that particular site. And that solves it. The only thing that's specific to the site is the installation file. The code is identical, which means you can have one code tree, and when you make a fix, you put it in once, and when you make an enhancement, you put it in once, and all of the site policies are defined in an individual file that you send out to the customer. You can do better than that. If you have every site that you sell to has a site license, the policy object can make a request over the internet and say, what is the value of this particular thing for site license X31PJJ6? And it can get it back from your headquarters. So if we have a company and we're selling this to 15 different customers, we, in this particular case, we're always involved with support. We know that they're using the application. We're in communication with them. If they say we want to make a change, they don't have to make it. They just let us know what it is. We make the change. And the next time the site policy object says, what's the value of, number of courses a student can take, it goes upstream and it says, I'm site licensed, whatever, what's that value? We return that value and it then returns it to the application object that was asking for the value. The point being that you can have an installation script where you can go upstream to the corporate headquarters to get the value. The only one that knows you're doing that is the site policy object. None of the other objects in your application has to know or worry about it. And that is a typical use of a design pattern. To be able to solve a problem that you have using previous thinking of the software architects that have gone before you. Until design patterns came along, science advanced. One generation would stand on the shoulders of the preceding generation. In software architecture, it was one generation would stand on the feet of the preceding generation. You never got up very high and you were always tripping and falling over each other. With design patterns, we are also at the stand on the shoulders level. You get to reuse that thinking. So the question, you've seen a little bit about how software architecture works, what the software architect does when they stare at the ceiling and then go out to lunch. In terms of making your career, even if you decide that you don't want to be a software architect, you're going to focus on the programming aspects of it. Knowing about design patterns makes you a better programmer. Knowing about software architecture makes you a better programmer because you now understand more than the objects that you're doing. You understand where it fits into the overall system, and you understand how to go and talk to the customer and find out what they really want, which if you're building an application is always a strong thing. So in answer to the question, can you be a software architect? Let me refer back to a former president who I deeply miss. Can you architect a software application? You can do it. Yes, you can. Thank you.
Well, thank you, Ron, for bringing that one home for us. Wrapping up the part 2 of your presentation. Welcome back.
Thank you.
Yes, and back in the library again.
Indeed.
Yeah. So a couple questions. Can a software architect effectively apply identical techniques to any software project?
So that's a fair question. And when you talk about a software architect, typically there's an adjective in the front of that. So you might be a retail software architect, or you might be a transportation software architect, or an education, or a healthcare, or insurance. It's very much you're in a domain, and these applications are in a domain, and the reason for that is that you're usually operating in an enterprise environment, and the applications that run in an enterprise are usually very different depending on what domain, what industry that application is running in, what industry that enterprise is in. It would be as if you said, well, you're an architect who designs skyscrapers, and now I'm going to get you to design a bridge. A different set of skills are necessary. So that's one qualification on the types of applications that you might architect. Typically, you'll be architecting applications that are within the same domain, in the same industry, because that's your area of expertise. The second distinction is really the type of application. The only things that carry forward across all applications are things like, what security model are you going to use? Are you going to deploy it in the data center or in the cloud? those kind of decisions. But application-specific decisions, there really are two kinds of applications that get architected. One is I'm in the Silicon Valley. There's one type of application that's a Valley application. It's the user runs it directly and it runs alone. And that includes big applications like Facebook and Google. But it includes even small applications. Someone sits at a browser and calls up this application. You're designing that. That doesn't necessarily have to be as well architected as the kind of applications that run in an environment that is an enterprise and have to operate within the enterprise environment. When you're developing an application that runs alone, your goal is eyeball capture. Get as many people to see it, send it out there. If it breaks, that's fine. We'll get feedback from our customers, and that's how we grow. We get it out and get it used and learn by that way. If you're in an enterprise environment where your application is one of 30 that make the enterprise run, that's exactly what you don't want to do. You don't want to get it out there and get feedback if it crashed, because if it crashed or didn't work, the enterprise can't do business. So if you have a pilot scheduling system, which is a very complex thing for a travel company or an airline, and suddenly snow happens and that pilot couldn't get to the next airport, so the next flight doesn't leave, and your application didn't handle that well, you've now shut down the airline. And so you're architecting not for eyeball capture, but you're architecting for it has to work and it has to seamlessly fit in. And then within the industry, you're architecting it for the airline industry or the education industry or so on. So in answer to that question, it is some things are generic and you can, like security and all the rest of it. Other things are domain specific and have to be architected by someone who is familiar with that domain.
Yep. Thinking about the flight control system and agile programming where, changes are made, whatever your sprint cycle is, like every week or every 2 weeks, how does that fit into a system like a aircraft control scheduling where it needs to run continuously, but it needs to work, but it also needs to be improved?
So the real agile programming is it's great, and it is really useful in terms of the applications that run standalone. You're always adding features. You're doing these releases. The product is changing on a weekly basis. That's an environment that doesn't happen at an airline. Give you an example. Southwest when they created Southwest, they picked up their pilot management system and their plane management system, making sure that there was always a pilot and a plane for every flight and all the rest of that. They picked it up from a different carrier, and there was a difference between that carrier and Southwest. The carrier they picked it up from had a hub. It was hub based. So there was Atlanta, and all the flights flew into Atlanta and left from Atlanta, which meant that it was much easier for them to deal with disasters or things going wrong, because the hub always had spare pilots and spare planes. They used that for Southwest, which didn't have hubs. And when Christmas time came and there was snow, people were snowed in, that application couldn't correct, because in fact it's like trying to fix a plane while you're flying it. Things were breaking. They had no spare pilot that they could get to, and when they did, that broke other things. They had to shut the entire system down over Christmas for 3 days while they actually fixed the problem and got everything back to flying. That was an example of an application that you can't on the fly tweak. It has to just run. And when you introduce new things into an application like that, it's why a lot of companies have applications that date back to 2000 and COBOL, because they can't really get rid of it while they're running. So the agile programming methodology doesn't really apply to applications that are running in an environment where everything has to be stable, and change can be a nightmare, because you have to literally go offline to make the change, and you can't. or the change is needed at Christmas time when everybody's stressing the system anyway. So yeah, agile programming works certainly for standalone. It's the best way to do it. But when you're dealing with a product that is getting installed and has to work and in a very stable environment, bi-weekly upgrades make no sense. It just can't happen in that environment.
We certainly know that no changes are allowed anywhere around the holidays.
Right.
Yeah. So back to design patterns. Are there best design patterns? Do you have favorite design patterns? Do you recommend certain design patterns to really know well?
Well, some are more useful than others, and of course, when you have a design pattern, a lot of people want to try to create new ones, even if they're not particularly needed. That's especially useful if you're writing a PhD thesis, and that your pattern may not be that involved. I mean, in terms of my favorites, um, uh, inheritance. Now that's actually a good example. Inheritance is an algorithm. I mean, it's a thing that you can do, and programmers can say, well, I know how to do inheritance. I can how to program that, and I know why. I know what inheritance is, reusing implementation from a parent class. The design pattern is specialization. And what the design pattern brings to it is it says, okay, you know how to use inheritance and you know and you know what it is, but you don't know when to use it. And so the design pattern is all about you're trying to architect a system and you need something like this, and now it's time to use it. So specialization is a design pattern that uses inheritance, but it uses it when it's needed. And sometimes you don't need it. And there are qualifications for that. You know, are the number of subclasses huge? Are the number of subclasses going to grow in the future? Are the impact of the subclasses on the things that the parent class does multiple things? So you want to replace, 30 switch statements, which got to modify each time with one pattern. That's one. Actually, I was going to talk about others, but let me just give you an example of when that design pattern is fantastic. You're writing an application for Windows, like a spreadsheet. And one of the things that a spreadsheet can do is cut and paste with every other application on that window. How is that possible? The developers of the spreadsheet never met the developers of the other applications. How is it possible that you can cut from a Word document and put it right into a spreadsheet when the two of them never met? And the answer is they're both children. They both inherit from window, and window defines the interface, cut and paste. So every window on that screen is implementing the interface that was designed by the parent. And what you get is universal interoperability because you've used inheritance to do that. Because every application is writing a child of the abstract window parent. And that's a design pattern that allows 1,000 applications all to interoperate without any of the developers ever having met. So that would be a good example of a design pattern that is called for in that instance. But just knowing about inheritance doesn't tell you how useful it's going to be in that situation. If that makes sense.
Right. And we all copy paste.
Copy paste, and it just works.
Yes.
How is that
Right.
even possible, right? Well, there's a design pattern there.
Right. It's at the end of the day, software is always implemented in some development language, programming language. You mentioned COBOL to begin with. Does that matter to the architect, the underlying language that's used to implement a system?
Yes. Ideally, the programmer would be familiar with the language. That's not a critical thing. The main issue is that the language has to be able to express the ideas that the programmer has. Clearly, if you're coding in assembly language, software architecture isn't the thing, and you've just got to figure out how to get that to work. The first language, and I was working in the industry when it came, I mean, you had BASIC, you had Fortran, and then C came along. And there were a lot of things about C that suddenly enabled higher level thinking. And the big one was the structure. And what it meant, you could say, I have a student, and you could say that student has a name, which is a character array. That student has an integer, which is the student ID, and it has a float, which is the grade point average. And you could put all of those things together, in a structure. And the language allows you to do that. It allows you to have arrays of that structure, pointers to that structure, arrays of pointers to that structure. And suddenly the word student meant something to the programmer. So the architect would say student, and the program would kind of have this thing that represented what the programmer's vision of the student was. C was the launch point, and from C came post-incremented C or C++, where you got into objects, and objects brought two things to the table. One, they allowed you to define not only what fields constituted a student, but they allowed you to define what you could ask a student to do and put all of that behind a wall. So the student suddenly became an object. It had an interface. You could say, enroll yourself in that section. And the code to enroll yourself in that section, the programmer knew exactly where that was. There was a method in student, public method that said enroll in section. And all of the requirements that you needed to enroll in a section, like you have to be paid up and you have to have all the prerequisites and you can't have a schedule conflict. All of that was located within student. The logic literally went to the abstraction and fleshed it out. And so the using an object-oriented language is the thing that you really want to do for an architect. You'd want to have an object-oriented language, because now you can say to the programmer, here are the things that go inside that abstraction. Here are the things that abstraction must do, and here is the encapsulation of all of that logic, and the data is all hidden. You can change any of that as long as you don't change the interface. And the architect is defining the interface. And so it's much easier for a programmer to be able to implement that interface in an object-oriented language. So in that sense, it matters. But whether you're using C++ or C# or Java or Python, it's kind of hazy. The ultimate evolution of languages, from Fortran to C, to C++, Python, the next level is with AI tools. We're hoping as architects will be English. And so you can literally define your system and have large parts of it delivered by the ChatGPT. Not that I've got anything against programmers doing that, but you can see the evolution, that the next programming language down the road a little bit could very well be English or Chinese, or whatever the architect and the end user is speaking.
Yeah, I was going to ask you about these large language models, and do you have sort of predictions of the future of how the steps we might take to getting toward perhaps, common language, spoken language becomes the interface? Have you thought about how ChatGPT and its, compatriots will get used in software development and then also in software architecture, what those steps might be?
Well, that this is an interesting moment in time. We've talked about three great revolutions that occurred in computer science. The first was the computer. And when the computer came in, I was in college, and we knew more about the computers than our instructors did. And at that time, the instructors knew, there were math instructors, and they knew about algorithms, but they didn't know how a computer worked. The second revolution was the web. And that was an interesting time also, because people knew how to set up websites and everything, and computer science instructors didn't know that. It wasn't part of their training. And eventually they caught up. And this is the third great revolution, AI, artificial intelligence. And we're scrambling. I am sure that I teach, and I'm sure there's students in my class that know more about AI than I do, although I'm trying to learn. And one of the ways I do that is by asking my students, if you can't forbid the use of what's going to be the big tool of the future. Just like you couldn't forbid the use of websites if you were an instructor. But I'm asking them, how do you use it, and trying to understand how they use it, and basically so I can teach and people how to incorporate that into what they're doing. They're getting better and better. I mean, you can use Copilot, and I mean, a quick thing. I said, give me a bubble sort in C++, and I got back the bubble sort in C++. It was commented. There was a step in there I hadn't seen when I coded it myself, and there was an explanation of why you really didn't want to use the bubble sort, because it was inefficient. Pretty impressive. What's going to be? It's like trying to forbid people from using a calculator when you give them a long division problem. It's just what you want to do, and so understanding it, I get the feeling is people that understand it right now better than I do. But in terms of the future and looking back on the previous two revolutions, it's coming. Every industry, every company is going to have it. In fact, has. They're worried about. They worried about how do we use a computer, how do we use the web. Now they're worried about how do I use AI, and it is a universal revolution. It's bigger than the Internet of Things. It's bigger than virtual reality. It's just affects everything, and we're going to see huge systemic changes to the programming profession, probably within the next 5 years. In terms of coming up from the bottom, I think we talk about encapsulation, about getting a design and making a bunch of objects that do certain things and then putting them together and architecting a solution based on these modules. What we're going to find is that I think AI is going to be able to do a great job of developing those modules because the interface is all there. You can have someone implement an objects within a well-architected system, never having to talk to anybody else on the project except the architect, which means if you can, as AI grows, you imagine those descriptions, the architect or someone else, the prompt engineer, can describe those modules to the point that they can be implemented by AI. And then, putting that together in a system, that might be the future. I've got 8 objects in this application, and 3 of them were done by AI, and the others were done by programmers who used Copilot to develop them. And that, I think, is where we might see the kind of applications that we're discussing go, the kind of applications that run inside of an enterprise. The excitement is those are the applications that have to work. And what you don't want is to distribute software that has AI hallucinations in it. So it really doesn't quite work. You want to get that right. So we're a ways from it, but you can see it. The crystal ball, you can kind of see what's down the road a couple of years.
Yeah, and you're getting into like prompt engineering. You mentioned the term prompt engineer. What is that?
So a prompt engineer, it's new, it's brand new, and everybody kind of has their own definitions. It's so think about how someone might use AI in a quick application. So you have an HR department, and they answer a lot of questions. And so what you do, prompt engineer feeds into triple quotes the entire HR manual for the company. 700 pages, puts it in there, and that's the only thing that AI knows, right? And then now you can ask questions like, does the healthcare plan cover glasses? How long do I have to work here to get 3 weeks vacation? Whatever question you would normally call up and ask HR, and the AI thing can answer that because it's been trained on the HR document. Now, again, it doesn't quite work that way because, like the functional spec, it's not quite right. It's mushy. There are ways that you can misinterpret. So the prompt engineer has to take that, do what I was doing during the demo, the lecture. Take what's a functional
Staring at the
specification,
ceiling?
stare at the ceiling, and say, you have to get the words right. We need to change this and that and this. And now we give it to the AI, and now we've got ourselves HR experts that can go exactly from so the AI expert becomes the HR expert becomes the customer saying, yeah, that makes sense. This doesn't make sense, right? And you're getting it right because the prompt engineer knows not what the programmers need to know, but what the AI needs to know in order to be able to answer these things. So that's kind of one of the things about prompt engineering. What you're doing, though, what's your programming language if you're a prompt engineer? Programming language is English. right? That's what you're programming the AI in. So, but it's knowing what the AI needs to know in order to do that job. That tends to map from software architecture over to prompt engineering more than, say, programming does, because you're trying to get the vocabulary right, which is what I was talking about in the session.
Yeah, words matter, right?
Words matter.
Words matter. Just,
And
yeah.
meanings matter, and definitions matter. So if you say seat, right? If you're on an airline, that's has an ID and you sell it and it's got a class and a position, and some have more legroom. A seat in a section has none of those things, but yet it's a part of the application, and you have to understand what it means in the context of what application you're dealing with. And that, I think, is going to be the underlying thing to get right for prompt engineering, which is very much like software architect. I think that's going to be the future, but we'll see, obviously.
Well, thank you, Ron. And I think we
Sure.
have Peter who's joining us to take us home. Can we hear you, Peter?
It's been a very long morning. So thank you, Ron. Thank you,
Sure.
Tammy, Juval and Keith. Thank them also. They're long gone. By way of just sort of crazy explanations, obviously we're going to have an interesting retrospective when this is over. You know, we live out here in Borrego Deserts. One of the things I said in the intro, which I think you lost at the very end, I said, and I'll be back at the end of the conference to congratulate us on what a great job we did. Well, unfortunately, not only did you miss that, you also, you know, now of course I'm not going to be congratulating us on what a great job we did. I spent the last 3 hours like staring at little square boxes that are turning from like orange to red to green to orange to red to green. So, gosh, with that all said, certainly really happy we did this. I actually have all the recordings now live in 4K, which I uploaded a couple of days ago. You know, I'm sure you recognize that all the recordings, all the sessions were recorded, but the Q&A. So you can head over there. When I'm done talking, I'm just going to share my screen to show the playlist that has all the sessions on them. But you know, you're on the channel now, so you can just click on the playlist and you'll see the latest one has all those sessions. I will encode the Q&A later and add that to this playlist. So if you subscribe to the channel, you'll probably get notified when I've added those. It takes me a day or two to get those all together. And I suppose that's about it. Thank you all for watching, and see you next time.
Take care.